In this last section of this unit, we are going to talk about graphing. What is the purpose of a graph? Well, there are a couple. One is to display experimental data to show how two variables are related to one another. Another is to allow the scientists to analyze the data. What kinds of graphs exist? I'm sure you've seen lots in your academic career. There are line graphs, there are bar graphs, there are pie charts. In this class, we're going to focus pretty much on a scatter plot. And a scatter plot shows values of two variables that are plotted on two axes, the x and y axes, and the pattern of the points show how the two variables are correlated to each other. Let's do an example. Here's an experiment. A rocket scientist measured the distance traveled by a missile at various time intervals and obtained the following data. Time is measured in seconds, distance is measured in meters. Which is the independent variable? The definition of the independent variable is a variable the scientist controls. If you, as the scientist in the laboratory, get to pick values of a variable, that's the independent variable. In this case, it is time, because the scientist chose 1 second intervals. Which is the dependent variable? The dependent variable is defined as the variable that is measured, or the outcome. Obviously, the dependent variable depends on the independent variable. In this case, that was distance. How are the two variables related? Well, in this experiment, as time, the independent variable increased, distance, the dependent variable, increased as well. Now, I would like you to pause this video, go back to the topics box, and watch the video entitled How to Create a Scatter Plot Using the Graphical Analysis iPad app. When you come back, I will show you the result of a scatter plot of these data, and we will talk about what we learned from it. Okay, welcome back. Here is what a complete scatter plot should look like. I have time, the independent variable, on the x or horizontal axis. I have distance, the dependent variable, on the vertical or y-axis. I have an informative title. Distance traveled is a function of time. A good general title for a scatter plot is how the dependent variable depends on the independent variable. How distance depends on time. I applied a proportional curve fit, which gave me the equation y equals ax, and the value of a of 376. Okay? I applied a proportional curve fit because this graph shows me that distance is directly proportional to time. As time, the independent variable increases, distance, the dependent variable increases in a linear fashion, and the y-intercept equals 0. Notice that the curve goes through the origin, meaning the point 0, 0 is on the line. When two variables are directly proportional to one another, what that's going to look like is the following. Graphically, as x increases, y increases in a linear fashion, and it goes to the origin. Algebraically, we saw from the curve fit, it gave us the equation y equals a times x, where a is the proportionality constant. Now, we're not using y and x, we're using distance and time, so we write this as distance equals proportionality constant times time. This is using the actual variables involved in the experiment. Okay? Now, here's a question. A, the proportionality constant, is the slope on the line. What's the unit on the slope? Do slopes have units? They do. Check this out. Distance is in meters. Time is in seconds. In order for units to work out, the slope must have units of meters per second. Okay? So the question is, what is the physical significance? The physical significance, it is simply the velocity, because velocity tells you how distance depends upon time. So I'm actually going to go back and modify this by replacing a with the symbol v. Now, from our scatter plot, we've obtained a mathematical equation that tells how these variables are related to each other. Okay? And we can use this now to solve problems. One type of problem is called interpolation. Interpolation is predicting the value of a variable within the range of those measured. And here's an example. What distance will the missile travel after 3.45 seconds? Again, we follow our process. We start by writing down the equation that we're given. Distance equals velocity times time. We are trying to find the distance, so we don't need to do any algebraic manipulation. I can simply, after writing the equation down, plug in the values. Velocity, remember, is the slope, which we said was 376 meters per second, times a time of 3.45 seconds. Seconds cancel seconds. And for my final result, I get the distance equals 1,297.20. We have to pay attention to sig figs, and each of the two measurements we used, both the velocity and the time, had three significant figures. So I'm going to round this to three significant figures. Looks like this is one of those examples where I need to use scientific notation in order to express it to the correct number of sig figs, 1.30 times 10 to the third meters as my final result. Another type of problem is extrapolation, and that's when we use the equation to predict the value of a variable outside the range of those measured. And here's an example. How long will it take the missile to travel 2,355 meters? Well, once again, I'll start with my equation. Distance equals velocity times time. I know the velocity, I know the distance. Now I'm trying to solve for time. So before I plug in, I will algebraically rearrange by dividing both sides by velocity. Don't know what that was. By dividing both sides by velocity. And velocity cancels velocity, and I have my rearranged equation, time equals distance over velocity. Now I'll plug in, my distance is 2,355 meters, my velocity is 376 meters per second, to give me a time of 6.26 seconds. And I'll draw a box around it. Okay. Let's take another example. Here's an experiment. I take 100 gram samples of 5 different metals. I measure the volume that each 100 gram sample occupies in milliliters, and I graph volume as a function of density. So the metals I chose are iron, copper, lead, mercury, and gold. And the question is, when mass is held constant, how does the volume change as the density increases? Well, we can see that as I go down the list, I'm increasing the density, but the volume is actually getting smaller. So I'll say, as density increases, volume decreases. In this case, the independent variable is density, because I, as the scientist, chose these 5 metals, and in choosing these 5 metals, I chose their densities. Which is the dependent variable? The dependent variable is the outcome that you measure, which in this case is the volume. Again, if you go to the graphical analysis iPad app and create a scatter plot, you will see something that looks quite different, as a matter of fact. Let's highlight this. We see density, the independent variable, in grams per milliliter on the horizontal or x-axis. We see volume, the dependent variable, on the vertical or y-axis. Volume is a function of density is a good title. Now we apply an inverse curve fit that gives us an equation y equals a over x, the value of a being 99.912. Okay? We say, based on the appearance of the graph, that volume is inversely proportional to density. As density increases, volume, the dependent variable, decreases. And when two variables are inversely proportional to one another, you will always see something that looks like this. As x, the independent variable increases, y, the dependent variable, decreases. Algebraically, what that looks like is, well, the equation was y equals a over x, or I can rewrite that as y times x equals a. What's the unit on the proportionality constant? Y in volume was milliliters. X, the density, was in grams per milliliter. So in order for the units to work out, that must mean that the unit on the proportionality constant is grams. Well, once again, I'm going to rewrite this using the actual variables we have. I'm going to write this as volume times density equals mass. And the physical significance of the proportionality constant in this case is mass. And that makes perfect sense because we said we started out with 100 gram samples of the 5 different metals. That's what's being held constant. And we see from the curve fit that the proportionality constant A, 99.912, is very close to 100 grams. So, to summarize, there are 3 ways in this class in which you will see variables related to each other. If y and x are directly proportional, then as x increases, y increases in a linear fashion and the line goes through the origin. And the equation is y equals a times x, where a is the proportionality constant. On the other hand, if y and x are inversely proportional to each other, then as x, the independent variable, increases, y, the dependent variable, decreases, and the relationship is y times x is equal to constant. There is a third type of relationship we'll see this year, which is a linear relationship. And if y is linearly related to x, then you'll see that as x, the independent variable, increases, y, the dependent variable, increases in a linear fashion, but the y-intercept is not equal to 0. And the equation is, of course, y equals mx plus b, where m is the slope and b is the y-intercept. So, to summarize, here is what I expect you to be able to do. Given a verbal description of a scientific experiment, identify the independent variable, the dependent variable, create a scatter plot using the graphical analysis app, and apply the appropriate curve fit. Describe the relationship between the variables as directly proportional, inversely proportional, or a linear relationship. Write the mathematical equation to relate the variables using the actual variables in the experiment, not just x and y. And then use the equation to solve extrapolation or interpolation problems. And that's pretty much it.